In this last video of Chapter 5, we will use the relationship between empirical formula and its mass and the molar mass to determine the molecular formula for a compound. Now we talked about how empirical formulas give the ratio between atoms in the molecule, not really the full molecular formula. It's a simplified, so the smallest ratio between the atoms. However, the molecular formula might be a multiple of that empirical formula. There are cases where different compounds can actually have the same empirical formula. This happens a lot, especially with hydrocarbons, for example. They simplify to same empirical formulas, but their molecular formulas and therefore their molar masses are going to be different. And we're going to learn how to calculate or figure out the molecular formula if you have the empirical formula and the molar mass of the compound. So if we want to do that, we need the molar mass and the empirical formula, because this is the formula that gives us their relationship. So if I have the molar mass of a compound and I divide it by the molar mass of just the empirical formula, it will give me this number n. Should be very close to integer. If it isn't a whole number, then we round close enough. So if it's really close to the integer in the lower end, so 2.2, let's say, or 2.3, we can round down to 2. If it's really high, so if it's 2.8 or 2.9, we can round up to 3. And this then becomes the multiplier for the empirical formula to get the true molecular formula from that. So n is the number of empirical formula units, how many empirical formulas are contained within a molecular formula. These are a lot of words, but let's kind of take a look at an example to help us see that better. So what is the molecular formula of a compound that has an empirical formula of CH and its molar mass is approximately 78 grams per mole? Now, if this is the empirical formula and I figure out what the molar mass is of just this empirical formula, it's not going to be anywhere near 78 grams. And that's why this is a simplified version of the true molecular formula. So I am given the molar mass of 78 grams. So it tells me the molar mass of that compound is 78 grams. That goes on top. And I just have to calculate what the molar mass of just the empirical formula is. I can do that very easily. We learned how to do that. I can go to the periodic table and look up how much a carbon weighs, or a mole of carbon. We can talk about either way, but I only have one, right? 1 mole of carbons for this empirical formula. So this will be 12.01. If I go to hydrogen, because I only have one, this will be 1.008. So if I add these two together, I should get approximately 13.018 grams. So this is the mass of just my empirical formula. The molar mass is given to me in the problem as 78, and that goes on top. So if I divide the molar mass by the molar mass of the empirical formula, I get approximately, so 5.99 or 6. That means that there are 6 empirical formulas contained in my molecular formula of the compound that I'm looking for. That means that there are 6 CHs in that particular molecular formula. And now to get the true formula, what I have to do is multiply each subscript of my empirical formula by 6. It just so happens that both of these are 1. And therefore, all I have to do is take the 1, which is the subscript of the carbon in my empirical formula, and multiply it by 6 by this number, and it will give me C6. I do the same thing for hydrogen, and it's the same thing because these are 1-to-1 ratios, so I have 1 carbon for every 1 hydrogen. And if I multiply them by 6, the ratio doesn't change, it's still 1-to-1. And my molecular formula then becomes C6H6. To double check yourself to see if you have done this correctly, you can calculate the molar mass of this compound, and it should be approximately, you guessed it, it should be about 78 grams. So go ahead and try that. Figure out how much C6H6 weighs. See if it is approximately 78 grams per mole. Here is a slightly different example problem that I'm going to work for you. It's a little more involved, but it follows the same lines. Okay, so let's determine the empirical formula of a compound that has this composition. It's 30.45% nitrogen and 69.55% oxygen by mass. Given that the molar mass of the compound is approximately 92 grams per mole, determine the molecular formula of the compound. So in this problem, we not only do we have to calculate the molecular, or to figure out the molecular formula, but we also have to determine the empirical formula first. And we do that by these percentages that are given to us. We assume a mass of 100 grams just to make our math easier, and we already talked about this. But if we assume a mass of 100 grams, why we do that? Because our percentages equal up to 100%. And so if I assume 100 grams, that makes my math easier. The empirical formula of this compound consists of nitrogen and oxygen because it tells me that it only contains nitrogen and oxygen, nothing else. I don't know these subscripts, so I can just say NX, OY. I'm going to look for these X and Y first. Okay? Now, how much does nitrogen and oxygen weigh? Well, nitrogen, if I go to the periodic table, weighs 14.01 grams, and oxygen weighs 14.00 grams per mole, respectively. Now, if I have 100 grams of that compound, that's why I assume 100 grams, that has these percentages, that means that I can say I have 30.45 grams of nitrogen and 69.55 grams of oxygen in that 100 grams of my compound. That's why we assume 100 grams, because we can convert these percentages in just amounts in grams, but the numbers don't change. It just makes the math easier. Now that I know that this is how much each of these weigh, so how much nitrogen I have in grams and oxygen I have in grams, I can convert these to moles because in an empirical formula or a molecular formula, these subscripts are molar coefficients. They give me molar ratios, not gram ratios. So I first need to convert these from grams to moles. And here's how I do that. I take the amount that I'm given, always start with the amount that you're given. 30.45 grams of nitrogen. I want to convert it to moles. So my moles will go on the top, right? And my mass of nitrogen from the periodic table will go to the bottom. So this is my conversion factor from the periodic table to go either from grams to moles or moles to grams. In this case, I'm going from grams to moles, and so I want moles on top and grams at the bottom. My grams, therefore, will cancel. Then I have 30.45 times 1 mole divided by 14.01 gives me 2.173 moles of nitrogen. I can do the same for oxygen, except I have to use the correct molar mass. So here it is. Start with the amount you're given, 69.55 grams of oxygen. I'm converting into moles of oxygen, so I multiply that by my conversion factor, which has moles at the top and grams at the bottom. My grams of oxygen are going to cancel, leaving me with moles on top. 69.55 times 1 mole divided by 16 gives me 4.347 moles of oxygen. So I found my coefficients, x and y. So I can plug these numbers for x and y. And here's my formula, my empirical formula, N 2.173, O 4.347. Now, as you can see, this isn't exactly correct because these can be simplified and they're not whole numbers. To do that, when I'm looking at, okay, this many moles of nitrogen, these many moles of oxygen, well, how do I simplify this? Well, I find the coefficient that is the smallest out of these two, or if I had another element over here with its own coefficient, out of the three. And I divide every subscript by that number. So in this case, the smallest of the two is 2.173. So I divide 2.173 by itself to give me 1. And I divide 4.347 by 2.173 to give me 2. So now I've simplified the coefficients to N1, although I don't write the 1, but it's N1O2. And it's a good empirical formula because I can't simplify it any further. And the numbers, the subscripts, even though this isn't written and it's 1, but these are whole numbers, not decimals like these here. That's why we do these. We divide by the smallest of the coefficients, but we divide through everything by the same number. So now I have the empirical formula. I have one more thing to do. I need to figure out the molecular formula. The problem told me that the molar mass of my compound is 92 grams per mole. How much does my empirical formula weigh? Well, 1 nitrogen is 14.01 grams per mole, but I have 2 oxygen, so I have to add to the nitrogen mass. I add the mass of oxygen, but I have 2 of those. So I have plus 2 oxygens. Each of them weighs 16 grams per mole. This gives me 32 plus 14.01, a mass of 46.01 grams per mole. That is my mass of the empirical formula that I just calculated. Now I can use that formula that was at the first slide of this video. So this is my molar mass divided by the mass of my empirical formula to tell me how many empirical formulas are in my molecular formula. There are 2 of them. Therefore, I have to multiply these subscripts by 2 to get the full molecular formula. I can take N multiplied by 2, so it's 1 times 2, giving me N2. And then the subscript for oxygen is 2 multiplied by 2, giving me 4. So my molecular formula is N2O4. N2O4 should have a molar mass. So if you do the calculations of the molar mass of N2O4, it should be approximately, once again, 92 grams per mole, because that's the molar mass that I'm given. Here's the sample problem for you to try. You have a compound that contains carbon, hydrogen, and oxygen. So you have 3 elements. And here are the percentages. 55.8% carbon, 37.18% oxygen, 7.02 hydrogen by mass. Assume 100 grams of your compound, and that will make these into grams instead of percent. Then you convert these to moles by using molar masses of each element, and then figure out which one is the smallest number in those molar coefficients. Divide through everything by that same number. That gives you the empirical formula of the compound. Figure out the molar mass of the empirical formula. Molar mass of the compound, the molecular formula is given here. Then you can figure out how many empirical formula units are contained in your molecular formula. Then multiply those molar coefficients of the empirical formula by that number to get you the molecular formula. Then if you want to double check yourself, calculate the mass of the molecular formula that you calculated and see if it comes out to be 86.08 grams. Okay, give it a try.